All right, so yeah, welcome back to the new season of the PBH Colloquium. It's a privilege to have Avi deliver the first talk. Avi, many of you know Avi, of course, but he's a professor of astronomy at Harvard, and he obtained his PhD in physics in 1986 at the Institute for Advanced Studies in Princeton. He was at the Hebrew University of Jerusalem, and then he was a long-term member of the Institute of Advanced Studies at Princeton. After coming to Harvard, he became director of the IPC at the CFA, so the Institute of Theory and Computation in 2007. And he serves currently as the head of the Galileo project from 2021. He was also the longest chair of Harvard Astronomy Department and also the founding director of this very institute. He's written many seminal papers on and reviews on first stars, first black holes, cosmic dark ages. And today he's going to talk about new insights on primordial black holes.
Thank you very much, Fabio. Usually in the future, just mention that I'm a curious farm boy. I was born on a farm. It will save us time. We don't need to waste. And so today I'll speak about a subject that is not often discussed, even at the BHI, and that is the smallest black holes that we can imagine, mini black holes. And over the past 6 months, I've written more than 6 papers on this subject, so I wanted to just summarize it here. And let me start with a historic footnote. In 2005, that was 20 years ago, I gave a lecture at the Hebrew University, a colloquium in Jerusalem, and Jacob Bekenstein was in the audience. And the title of my lecture was Imaging Black Holes. And as Shep remembers, back then, we started doing calculations with Avery Broderick and working together with Shep. And that was a new frontier, and I tried to express my enthusiasm. But Jacob came to me afterwards, and he was not impressed. he said, this is not such a big deal, what you're talking about, because besides of the patterns of turbulent accretion flow and jet formation around black holes, will we actually learn anything fundamentally new from imaging black holes that we do not know already? So as far as he's concerned, this was not as attractive. That was, frankly, his opinion. And since then, that struck me, because he was thinking about it from a basic principles approach, not so much from an astrophysics approach, the way I was. And so in this talk right here, I will try to address a question that I heard from Paul Davis, that John Wheeler posed in 1972 to Jacob Bekenstein when he was a PhD student at Princeton. And Bekenstein at the time, because of the work on black hole entropy, he was distracted. He couldn't address that question. And I just addressed it in a recent paper that I will describe here. And so I really wish that Jacob was here to hear this talk, and I would like to see if he appreciates this discussion more, because he was supposed to answer this question that I'll be addressing. And that has to do about quantum mechanical effects during the accretion of mini black holes. So what are these primordial black holes? Well, we know that in astrophysics, you can make a black hole either from the collapse of the core of a massive star or from the segregation of gas at the centers of galaxies. And in the smallest black holes we know about astrophysically are of the order of 3 times the mass of the sun, 3 solar masses. But if we want to make smaller black holes, we can't do it because there is not enough gravity in low mass stars to collapse the core to a black hole. It cannot overcome the pressure. The gravity is not strong enough. But in the early universe, we know if you take a portion of the universe that has a density above the critical density, meaning gravity is stronger than the kinetic energy of the expansion, so you end up with a bound region, then the expansion will end up in a contraction and collapse to a big crunch. We know cosmology allows solution like that, and all you need is a high enough mass density within a given region. So consider the horizon of the universe which has a size that is proportional to the cosmic time since the Big Bang. So it's the speed of light times the age of the universe. That's the horizon at any given time. So at early times, the horizon was small. And within that horizon, if there happens to be a density enhancement large enough, that region will end up collapsing. And it could collapse to a black hole if there is not enough rotation to prevent that. Now, you ask about numbers. Okay, so 10 microseconds after the Big Bang, the radius of the cosmic horizon was 3 kilometers, which is the size of the horizon of a solar mass black hole. And the radiation temperature at that time was 150 MeV, 300 times more than the electron rest mass. And the density, the mass density, was bigger than at the center of a neutron star, was 2 times 10 to the 16 grams per cubic centimeter. So there was a high enough density there, and if you just enhance it enough, the region will make a black hole of a solar mass, which is smaller than we can make astrophysically. And obviously, as you go to earlier time, you can make even smaller black holes. The only question is, how do you make these density perturbations? You can't just enhance the density by 10 to the minus 5, which is the standard scenario, because the collapse will never happen. So you really need some phase transition to do that. And people conjectured all kinds of processes that can do that. So in this, we don't know what 85% of the matter in the universe is. That's really humbling. We get paid to study the universe. And we get nice salaries here at Harvard, but very rarely would you find one of my colleagues admitting that they're not doing their job. For decades we are talking about what the universe contains, and we don't know what substance makes 85% of the matter. That's really a big failure. And since I started astrophysics, it was 40 years ago. Since then, people are talking about detecting the dark matter. It will come within a decade. 40 years, nothing. We don't know what the dark matter is. So we talk about it as if it's familiar, but actually it's completely unknown. We don't know what makes it. And one possibility is primordial black holes, because they would not interact with light if they're small enough, and we won't know about them. And so the standard picture is that there is some constituent made of elementary particles. That's the dark matter. We don't know what it is, and then it preserves memory of the initial density perturbations on galaxy scales. By the way, a footnote that many people don't know, I bet you if you go around, even at the CFA, people would not know that. We owe our existence to dark matter. Does everyone know that? Did you know that? Sure. No? We wouldn't exist if dark matter didn't exist. The reason is simple. The universe early on had adiabatic fluctuations, meaning that the fluctuations in density were the same in all constituents. Okay, so radiation, matter, they had the same fluctuations. We see that in the microwave background. Now, if there was only ordinary matter that is coupled to the microwave background, then what happens is when the universe was 400,000 years old, about a redshift of 1,000, the ordinary matter starts recombining to make hydrogen, and it decouples from the radiation. And then the radiation starts diffusing, and fluctuations on small scales are washed out. This is called silk damping. And fluctuations on galaxy scales are washed out completely. We can see that in the microwave background, that if you look at the baryonic oscillations, they are damped as you go to higher L's in the CMB fluctuation. So what that means is, if there was no dark matter, there wouldn't be any fluctuations on galaxy scales. The only reason we have galaxies like the Milky Way is because there was dark matter that was not coupled to the radiation. It had fluctuations, and those were not damped. So the Milky Way would not exist without dark matter, and therefore the sun would not exist without dark matter, and therefore the Earth would not exist, and we would not exist on the surface of this rock. So we owe our existence to dark matter. We should be grateful. But we still don't know what this matter is. And maybe it
has to be there, right? It has to be there.
Well, it depends who you ask. Some people say that gravity is modifying. could be modified, but as long as gravity is not modified at low accelerations, it has to be done. So one possibility is the universe had some phase transition early on, made primordial black holes. There is no new particle. And those primordial black holes are still around us. They are the dark matter. And frankly, if I had to bet, I would bet against it, because you really need to fine tune in converting a very specific fraction of the radiation energy density into matter. Otherwise, you make too much matter, but maybe it happened. That's possible. And so we should approach it from an empirical point of view. And there were many astrophysical constraints, and I worked on some of them over the past decade. So here is a summary. Black holes with a mass less than 10 to the 17 grams. So what you see on the top is the mass of the primordial black hole in grams. At the bottom, it's in units of solar masses. So below 10 to the 17 grams, or 10 to the minus 17 solar masses or so, that range is excluded because these black holes would evaporate. Either they would not exist. If they evaporate within the age of the universe, we won't find them today. That's decaying dark matter, if you want. But if they do still evaporate and exist in part today, they would produce too large of a gamma ray background. And we don't see that gamma ray background. So people were able to set this limit here. It's like a cliff. And you can see this means that it goes deeper than 10 to the minus 4. So you can't really make more than, I don't know, 10 millionth of the dark matter as you go to lower masses. But then above 10 to the 22 grams, or 10 to the minus 13 solar masses or so, microlensing sets limits. And microlensing is simply the brightening of a background star by a foreground lens. So if the dark matter was made of primordial black holes of these masses, we would have seen the signature of these black holes in the magnification of the background light from distant stars in the Milky Way galaxy, or in M31, the Andromeda galaxy. So it's quite a powerful limit, as you can see, and it's really impossible to avoid it because we know that the Milky Way has a dark halo. But then you are left with this window, and if anyone in the audience can rule out this window, that would be fantastic, because then I wouldn't have to give this talk anymore. But this is a wide window between 10 to 17 grams and 10 to 22, and the dark matter could be made by these. These are asteroid mass black holes. So if you consider an asteroid that with a size of 10 kilometers, like the one that killed the dinosaurs 66 million years ago, the mass was just around here, okay? That's the dinosaurs saw an object of this mass. They didn't anticipate it. They were not intelligent enough to build telescopes to warn themselves, so they're not around. We are thinking of ourselves as intelligent, and so we have a plan. If an asteroid that big will approach us, will become a near-Earth asteroid, we might nuke it or do whatever. Anyway, but we will not survive because of other reasons, probably, and you know, AI, pandemics. Who knows what awaits us in the future? That's a subject for Peter to worry about. But anyway, so these mini black holes here, you know, they formed very early on when the universe was, I don't know, a picosecond old. But they might be the dark matter here, and what can we say about them? So let me first mention a paper that just appeared a few days ago in the archive. Unfortunately, the title is blocked, but it's basically an interesting footnote about black holes. You know, perhaps someone in the audience thought about it, but it was never written down. And you can find it on the archive from last week. Basically, black holes, especially low mass black holes, rule out particles, messengers that move faster than light. So why is this interesting? Well, a lot of people in science fiction talk about going back in time, visiting your ancestors. It introduces some logical issues. You can go back and prevent your grandfather from meeting your grandmother. So how can you exist? You know, like this is the grandfather paradox. So you can build a time machine if it was possible. You can make a lot of money because transactions in Wall Street are traded at the speed of light. And some people get close to Wall Street to make transactions faster. But if you had a neutrino, as some people claimed a decade ago, that propagates faster than light, you could have made a lot of money communicating and making a transaction with a faster than light neutrino. Turned out that the Opera experiment at CERN had a faulty cable in the timing system. So it was not faster than light neutrinos that were announced. For those of you who were kids back then, there was an announcement by CERN that faster than light neutrinos may exist, and then they retracted that. But what we show here is that if tachyons, these are particles moving faster than light, exist, they must be lower mass. The high mass tachyons can be ruled out by the existence of black holes. And why is that? Well, tachyons have a different action than slower than light particles. This is the usual action, and then there is a minus sign introduced inside the square root and taken out of the front of this expression. And so if you consider tachyons, what you find is that when you plot the momentum of a tachyon versus its velocity, the velocity actually can diverge, go to infinity, be much larger than the speed of light if the energy goes to zero. Okay, and the way to see it is through the relation. The standard relation of energy and momentum is this one that you're all familiar from special relativity. And then for tachyons, you have this relation here. Now, in this work with Mark Hertzberg from Tufts, we realized that changing the relation for the energy as a function of momentum implies that Hawking evaporation would kill black holes if tachyons existed, if massive tachyons existed. And it simply comes from calculating the power emitted by Hawking radiation in the case of tachyons. And instead of getting the Hawking temperature to the fourth power in the power, like the black body radiation, the usual Hawking radiation is the area of the black hole times the black body brightness, which goes like temperature to the fourth, and the temperature is just corresponding to a de Broglie wavelength equal to the horizon size. That's why a black hole cannot be a prison quantum mechanically, because you can't imprison a prisoner that is too plump. Imagine a prisoner bigger than the size of your prison. You can't just push the prisoner in it. So particles with a wavelength bigger than the horizon escape. That was Hawking's result. But then if you include tachyons, what you find is you get more power for very heavy tachyons. And so for massless, you just get the standard expression for the lifetime of the black hole that scales as the mass of the black hole cubed. But for heavy tachyons, you basically get that the lifetime is shortened, and it scales as the inverse of the mass of the tachyon squared. So that means for very heavy tachyons, let's say approaching the GUT scale, 10 to the 15 GeV, 10 to the 15 times the mass of the proton, or the Planck scale, 10 to the 19 GeV, you will get a very short lifetime. In fact, we can rule this out from the existence of stellar mass black holes. And so when you plot the black hole lifetime as a function of the tachyon mass, you end up excluding tachyons with masses bigger than 3 times 10 to the 9 GeV, 3 billion times.
Are there any other constraints on the tachyon mass from?
No. So this, it's such a simple result. And again, I'm usually struck by the fact that I think about something and then we don't find it in the literature, because this should be simple. And then after we publish it, nobody pays attention because it's obvious. That's the other. So this is what you can do with the free solar mass black hole, which we know exists from LIGO and astrophysics. But if we had a primordial black hole, then we can push this down to even 7 GeV for primordial black hole in the range that can make the dark matter. So in principle, this basically says that massive tachyons can be excluded if you find black holes. The smaller the mass of the black hole, the better is the limit. Very simple result from last week. But what this question that John Wheeler posed to Bekenstein back in 1972 is the one that I addressed in a paper in the Astrophysical Journal Letters. And I should say I published it in UpJ Letters because there were moderators on the archive that blocked this paper. They basically were not convinced that it should be made public, and I couldn't submit it to JCAP, which requires an archive link. So I submitted to UpJ Letters, which is has the highest impact factor among all astrophysics journals. And the paper was accepted for publication by the chief editor of the Astrophysical Journal. And only then, around that time, the archive agreed to post it, which I find ridiculous in today's culture. I don't know if any of you had this experience. But how can the archive moderators do that? At any event, here is the argument. The Schwarzschild radius of a black hole in the range that can make the dark matter, let's say a few times 10 to the 19 grams, equals the Bohr radius of the hydrogen atom. What does that mean? It means that the approach taken by leaders in accretion physics around black holes, like Ramesh, for example, cannot be applied here, because imagine hydrogen atoms coming close to this black hole. They have a size comparable to the horizon of the black hole. You can't treat them in the fluid approximation. You can't do that. Yet, you go to the literature and people talk about these primordial black holes accreting just like big black holes in the fluid approximation, Bondi accretion. So I just wonder, how do you treat accretion for these mini black holes that could make up the dark matter? And you can make the black hole smaller, and then at a mass of around 6 times 10 to the 14 grams, which is just the mass where the black hole lifetime is comparable to the age of the universe, you get the Schwarzschild radius being equal to the proton size, the size of a proton. So even if you forget about atoms, a proton falling into a black hole that evaporates over the age of the universe is big. It's a plump prisoner. You can't just push it inside. It's bigger. It could be bigger than the horizon. So how do you deal with that quantum mechanically? That's the question that John Wheeler asked Bekenstein to solve, but he was distracted. So imagine a proton getting into a black hole because it's small enough, but the electron still has a wave function that is bigger. So in principle, you can imagine a black hole atom. So the only difference from the hydrogen atom, where the binding is by the electric force, is that here you have the electric force plus the gravitational force. Both of them in the Newtonian limit for gravity, both of them decline inversely with distance squared. So all you do is have a modified coupling constant that involves electric and gravitational for the electron, okay? And so it really depends on the mass of the primordial black hole that the proton ended up joining. And here the mass is expressed in units of 4 times 10 to the 15 grams. And if the mass is big enough, bigger than that, you can get a bound atom, a hydrogen-like atom that is smaller than the hydrogen atom because of gravity. And the binding energy will be higher than the standard Rydberg 13.6 electron volts because of gravity. So in principle, you can get an atom that has transitions at very different energy levels, depending on the mass of the primordial black hole. And really, the question is how long such an atom survives. By the way, this is an actual image of the hydrogen atom. And I can give you the reference. So that reminded me of another problem in nuclear physics, where you have a nucleus and you have a wave function of the electrons surrounding the nucleus in a bound configuration. And you ask, what's the rate by which the electron will be captured by a proton in the nucleus so that it converts the proton into a neutron. So an electron can join a proton and make a neutron in a nucleus. This is called K capture. And the chance for that is related to the overlap between the electron wave function and the volume of the nucleus. So it's easy to imagine the electron as a cloud, and there is some overlap of this cloud with the nucleus. And as a result, the electron spends some time inside the nucleus, and as a result, it gets absorbed by the proton, makes a neutron. So that's the way the K capture, the standard calculation, is done. And so I did the same thing for the black hole atom, except now, there is a characteristic speed of the electron cloud that is different. So that's this V here, and the size of the atom is the region of the electron wave function is different. And so when you ask what is the chance of the rate by which the electron will be absorbed by the proton sitting inside the black hole, you end up with a certain time scale using the same formalism. And from that, you get some accretion rate, because you will absorb a proton, and then after that, the electron will eventually decay. And the black hole will become neutral again. And you can imagine this successive process. The accretion rate is quite small in that case. So that's for bound states. But you can also ask, could the charge be much larger than a single proton? And the answer is yes, but there is a maximum charge in a plasma that I calculated, because eventually the electric energy becomes comparable to the thermal energy, so you can't make the charge even bigger. And that will enhance the rate of capture of electrons. But you can also imagine a situation with free electrons that are not bound to this primordial black hole. And then I did the calculation of the accretion rate, and it ends up being suppressed relative to bond accretion. And the suppression involves the velocity of the electron over the speed of light squared, and also the Schwarzschild radius relative to the inter-electron distance. So the answer is different from bond accretion, but I gave it so people can use it. And you might ask, where is accretion important? If that's the case, it turns out that it's important only inside stars. And actually, Hawking in 1971, before he came up with the idea of Hawking evaporation, he wrote a paper in 1971 trying to explain the solar neutrino problem. Many of you don't know what it is, but my early mentor, John Bacall, was obsessed with this problem for decades. That was his main focus. There are too few electron neutrinos observed from the sun. And by now we know it's because the electron neutrinos are converted to a different flavor, mu or tau. But back then it was not clear, and Stephen Hawking suggested, well, maybe there are fewer nuclear reactions taking place in the core of the sun because there is another power supplier, and the power supplier could be a primordial black hole sitting at the center of the sun, accreting mass. So that's a situation where the accretion has to be done quantum mechanically, but Hawking didn't do it. And in other stars, actually, the situation could be even better. Like if you consider white dwarfs that have 1 million times the mean density of the sun, or if you consider neutron stars that have 14 orders of magnitude more higher density than the sun. In those environments, the accretion is even more significant. So if you trap a primordial black hole inside stars, that's where these calculations are relevant. And in principle, if you trap a mini black hole inside a neutron star, it can turn it into a low mass black hole. So if LIGO observes, right now, anything below 2 solar masses is declared as a neutron star by LIGO. They don't know if it's a black hole or neutron star, but if in the future we'll be able to say, oh, actually, it was a black hole with less than 2 solar masses, one way to make it is by trapping a mini black hole at the core that will basically eat it up from the inside. It's sort of like being pregnant with a baby that eats you up. It sounds like a horror story, but this is what primordial black holes can do.
Avi, does this rule out Thorne-Zitkoff objects straight away?
It's really an interesting question of what happens. So Thorne-Zitkoff objects are, let's say, a black hole, astrophysical black hole gets absorbed into a bigger star. It's still an open question as to what happens, because, you know, once you start feeding the black hole, then it could create enough energy to basically destroy the star and not accrete anymore. Or it could eat up the star, and the verdict, I mean, it's very complicated to figure out which of these outcomes. I don't think it's a settled question. And perhaps with LSST and the Rubin Observatory, we'll be able to tell what happens to Thorne-Zitkoff objects. That's an interesting PhD.
Be a new source of transients if it's eating up the star.
In this case, it's different because you're starting with a very small black hole. Yeah.
Sure. Yeah.
You've been talking about particles being absorbed by the black hole.
Yes.
But these black holes could sit in a radiation bath. So
Right.
can
In
they
the
absorb
early
photons?
universe, yeah.
Can they absorb photons?
Yes, they
they're
can.
not as plump, right? Or
Yeah, so actually, it's interesting that you're asking, because there was a physical review letters paper published half a year ago claiming that black holes cannot be created out of light. I just saw the title, Black Holes Cannot Be Made Out of Light, and I immediately wrote to the editors, you know, a comment on this physical review letter saying that's wrong, because black holes in the early universe can grow out of light, you know. And then the editor said, well, it's not really relevant because they specify, you know, like a lawyer, they specified conditions that are not really as, the same as in the early, but I said, look, the title of the paper is Black Holes Cannot Be Made Out of Light. This is wrong. They made a press release about it. So once again, you know, something is wrong, not only with the archive, it's also wrong with the editors of PRL.
Does spectroscopic precision spectroscopy limit the prevalence of these primordial black hole atoms? So
we need enough light to be generated by those atoms. And as I said, well, if you make those atoms in the interstellar medium and there are enough of them, then it's interesting. I haven't checked the numbers.
There's new kinds of transitions, right?
And new transitions, yeah.
probably absorption.
Yeah.
It would be new. I haven't gone through the numbers if there are enough of them to create a detectable signal. Yes.
But
Okay.
Well, I just wanted to follow up. So, but could you get appreciable accretion through absorbing photons? And with that,
Only in the early universe when the density of radiation is high enough. But if you go to the numbers, it's not possible. I mean, of course, there is radiation also inside the sun and other stars, and you can absorb that. Yes, in stars you have enough, or in the early universe, but not in interstellar space. Yes.
Got a question. Okay.
Okay.
I mean, so which means, you know, a lot of us have been calculating this growth of these primordial black holes, are assuming that there's no growth till you reach the matter-dominated era. That's not really true then, right? There could be some.
That's
growth
right.
From
Yeah, definitely. I mean, the
radiation-dominated
initial
era.
collapse is in the radiation-dominated era. So obviously, you could. It depends how far the overdensity extends, because the rest is expanding with the rest of the universe. So yeah, in principle, you can have a lot of radiation falling in. Yeah, definitely. Yes.
The existence of those black hole atoms require the attractive force, well, the gravitational force is a lot.
Gravitational plus electric.
Plus-
Yeah. Yes.
Okay.
Yeah, both of them. And the only reason you can just worry about coupling is both of them decline as 1/r². So the Schrödinger equations solution is applicable. You just replace the electromagnetic coupling with also gravitation. We are in the Newtonian limit here. I'm not talking about the Planck scale. Okay. Finally, I wanted to mention that. Yeah.
Can you hit OK on that?
Ah, you mean at the
Because
top?
then we would see the title of the.
Actually, it doesn't appear on my
Oh,
thing, so it must be something unavoidable. Finally, I just wanted to comment that Hawking radiation would also lower the accretion because you will have this outpouring of energy that is suppressing accretion. But I did not even consider that. Okay, so now for the fun part, you should just consider it as a sort of brainstorming idea. Not, I'm not claiming this exists, but I just wanted to have some intellectual fun here. So what is the most efficient engine of clean energy? So suppose some of you are worried about the environment. You want an engine that with the new administration, I'm not, I have to be careful. But the best engine you can think about is 100% efficiency, converting rest mass to energy. 100%. Is that possible? Well, obviously, you think about matter and antimatter as fuel. The only problem is to make a microgram of antimatter, CERN has to invest, I don't know, $1 billion. So we cannot make the fuel of antimatter and fuel our economy with matter-antimatter annihilation at 100% efficiency. We just cannot do that. Is there an alternative? And my answer, yes. Black holes give you the perfect engine. You haven't thought about it, so let me explain. So the idea is, if you have a primordial black hole with 100,000 tons of mass, such a black hole would evaporate over 1.5 years. Okay? That's the Hawking evaporation time of a black hole with 100,000 tons. Just plug it into the Hawking formula. 1.5 years. Now, how do you prevent this black hole from disappearing? You just dump mass into it. How much do you need to preserve this mass? It's basically this much mass over 1.5 years. Mm-hmm. That ends up being 2.2 kilograms per second, which is what you get when you flush the toilet. So I was actually downstairs at the men's room, and it was written there. I could.
Avi, I hope you weren't doing measurements.
No, I didn't do anything. It was telling me actually how many liters are being dumped. 2.2 kilograms per second is what you get when you flush the toilet. So you just do that routinely. You flush the toilet on such a black hole. And then it's the perfect engine. Why? Because all the mass that you dump into it gets converted into Hawking radiation. So you take mass, convert it with 100% efficiency into clean energy. And you can do it forever. So I just wrote a research note saying that it's a way of an advanced civilization, but if they want to power their planet without having a companion star, they can just have a moon, a primordial black hole that is in a low Earth orbit of this mass will give them as much energy per unit area on their planet as the sun gives to Earth. The only question is, how do you trap 100,000 ton black hole in a moon-like orbit, low Earth orbit around the Earth? That remains to be seen.
Also, how you capture that energy output.
Yes, that's another, and I actually worked some numbers on that. So this is the calculation of how the 2 kilograms per second, and the temperature related to what Priya just asked is very high. The Hawking temperature is 10 to the 15 degrees Kelvin. So you need to surround it with some blanket of material that converts it into heat. This is the luminosity in solar luminosity. It's 10 to the minus 10 or so. And the issue is you can't, to make such a black hole, you really need 10 to the 60 grams per cubic centimeter. That's really difficult to do. And then how, but I calculated that when you consider the Klein-Shina cross-section for scattering of the radiation on electrons, this is actually sub-Eddington. This feeding rate of 2 kilograms per second is below the Eddington limit because the Thomson cross-section is reduced by the high energy of the photons. Anyway, this is just an anecdote. And then, if we ever see an exoplanet with a bright gamma ray moon around it that keeps it warm, well, maybe someone else thought about this idea.
But so I mean, based on what you said before, how
Yeah.
does it accrete?
Sorry?
How does
That's
it
the other challenge. Yes,
Okay.
that's a very good point. I agree. No, the reason I wrote the other paper is because I first came up with this idea, and then I started worrying about how it accretes. Yeah, so that's a very good point. Okay, what limits can we put on primordial black holes from the solar system? Well, if they're buzzing around from the halo of dark matter, they might cause fluctuations in the positions of planets near the sun. And I derived the kind of perturbations that one gets, and they're not very far from the current limits on how much the mass of the sun changed. By the way, if you wanted to know the record, the limit right now is at the level of 10 to the minus 14 solar masses per year. That's how much. So it turns out that the wind of the coming off the sun is detectable gravitationally. We see the mass of the sun being reduced over time by precise monitoring of the orbits of the planets. At the level of 10 to the minus 14 solar masses per year, we see those effects. But that also sets a limit on any intruder that may pass through the solar system.
Particles, or is that radiation that you're converting?
No, this limit is coming from the ephemeris of the planet. So it's basically gravity modified. If the sun had a fixed mass, the planets would follow particular orbits. You can tell that they are not. That in fact the orbits expand because the sun is losing mass. You can detect that in the ephemeris already. So the solar wind is accounted for not just by seeing it, but by detecting the gravitational influence.
So it's radiation and particles, right?
Yes, both of them, and neutrinos.
And
And neutrinos, yes. The radiation is not negligible. That's a good point, yes.
Because one can expect that even in all galaxies, right? When
Yes.
Capturing.
I wrote a paper a decade ago about the fact that galaxies expand because they lose rest mass through the radiation. Yes, but it's a small effect, at the level of percents.
Avi, is there any correlation in all of this with solar activity, the solar
The
cycle?
solar activity introduces short timescale variations, which are averaged out on the orbital times. I mean, it really depends which planet you're talking about. The inner planets can be sensitive to that. Okay, so here is a fun point. There is talk about another planet in the solar system. It's called Planet 9. And one of the people who advocated that is Konstantin Batygin, who used to be a postdoc next to my office at the ITC. The other one is Mike Brown from Caltech, and they both suggested there is a ninth planet based on the clustering of objects beyond Neptune in the outer solar system. So they see clustering is sort of like shepherding, and they claim there is a shepherd, that there is something that is triggering this clustering of trans-Neptunian objects. And this has to be a planet with 5 times the Earth mass. And it's about 500 times away from the sun than the Earth is. And they have been searching for that for almost a decade now. They haven't found it. So it occurred to me, okay, they haven't found it. Maybe it's a primordial black hole that makes some fraction of the dark matter and was captured by the solar system. And when Mike Brown heard about this, some reporter asked him about this paper. He said, well, it could also be a hamburger or something. I mean, which again shows you how observers are not willing to think seriously about fundamental physics. He would die just for the, he would not find anything and still insist. But the point is, we know there is dark matter. We know there are things we don't know what they are. So not everything is made of stone. I wasted a lot of my time over the past 5 years arguing with people that believe that everything in the sky is rocks. That's all you have. And the same is true about Mike Brown, about Planet 9. So I said, okay, what about a black hole? Now, how can you check if it's a black hole? Because there are icy rocks in the Oort cloud that every now and then will collide with a black hole. And you would see a flare. And in fact, we used one of Ramesh's advection-dominated accretion models, the RIA, to calculate the brightness of the flares. And we found that with the Rubin Observatory, you can find flares above the detection limit that are definitely, there are few of them per year. If Planet 9 is a black hole, you might see it flaring as a result of icy rocks colliding with that black hole. Finally, here is a paper that I wrote just because of an interesting coincidence. I realized that if you consider the Earth, okay, and you imagine an object passing within a distance that is comparable to the radius of the Earth, and if this object is moving close to the speed of light, turns out that you take the speed of light, divide by the radius of the Earth, you get 50 hertz. Does that remind anyone of anything interesting? 50 hertz is the frequency that LIGO is sensitive to. Okay? So you write down, I'm talking here about not detecting gravitational waves, but detecting the tidal force associated with a relativistic object passing near Earth. Tidal force, Newtonian gravity, you can write down for the tidal force, you can write down an equation that involves the strain in the metric. And as you know from tidal forces, it includes the distance cubed from the object passing through. So the distance is a function of time. If you imagine a straight line, there is a minimum distance that the object will pass from LIGO, let's say. LIGO is on the surface of the Earth. Okay, so there is some minimum distance. And then there is the angle between the path of, the angle between the axis connecting the object at any given time to LIGO and the direction of the arm of LIGO, of the interferometer. So there is some angle, and that angle is alpha here. So there is some dependence on cosine square alpha. This is the standard tidal force. There is nothing new here. It was known hundreds of years. So you just put in the standard tidal force formula into a relativistic equation that gives you the strain on an interferometer like LIGO. And you put numbers and you find that if this object has more than 10 to the 14 grams, the strain at a distance comparable to the radius of the Earth, the strain will be bigger than the sensitivity of LIGO. That's interesting. And I actually derived an exact solution to this equation for a straight line perturber. So this is the signal as a function of time. And if you see this signal in LIGO, you know that that must be it, because there is a very specific dependence on time in this. So it goes like t squared, and this is the frequency f that I wrote here. And beta is the speed of the object divided by the speed of light. R mean is the distance of closest approach to LIGO. M is the mass of the perturber. And then you can calculate the rate of such events depending on the number density of objects. And what you find is that the limit you can put by LIGO not detecting this signal says that the mass density of these objects need to be less than the dark matter mass density. So the conclusion from that, it's not earth shattering, it's not exciting in particular, but it basically says you can't have a mass density comparable to the dark matter in relativistic objects that have a mass above 10 to the 14 grams passing near Earth, because LIGO would have detected them. And not, the LIGO collaboration never pointed this out, by the way. Of course, it applies also to asteroids, but the asteroids do not move at the speed of light. They move with a beta much smaller, and therefore the frequency is much smaller. So you don't get, LIGO cannot detect asteroids.
Does that mean that Lisa?
But
have to
yes,
watch out for-
good point.
Oh, I see. No,
You're the smart kid in the class here.
Or also,
Give him a lollipop.
Excellent.
Avi, one could also do better with LIGO-like interferometers on the moon with no
Yes.
seismic noise. You can push that frequency.
That's
down.
right.
And
And
it's-
also Lisa and other space interferometers could get to a regime where we might put constraints on speeds much less than the speed of light, let's say 10 to the minus 3 or 10 minus 4, which means that we could detect the large asteroids gravitationally or dark matter objects if there are primordial black holes. We could. So this would be a new method to detect primordial black holes, I'm not sure that the LISA advocates are aware of that.
So I also wonder if LIGO is looking for this kind of signature.
I don't think so.
Because if
So what
they are
I'm-
not looking, then we don't even know if it's.
Yeah, we don't even know the waveform, right? I mean,
So, I
there's
mean-
no template. You have it there,
Here's
but
the
they don't
template.
have a template yet.
Yeah,
So-
well, I give it analytically,
Right.
so they can use it.
But if they are not looking for it, then we don't even know if
That's
it's in the
right.
data, right?
But okay, so then I hope they listen to this talk. So part of what I'm doing is trying to think about things that other people did not think about before, so that they can look into it. So my hope is, let me conclude with this slide, is that there is a mini black hole within the solar system or close to it, because then we can study quantum gravity experimentally. And that would be a great thing if it exists. I would love to go on an expedition to the vicinity of such a black hole towards
Not
the
too
end.
close.
Well, it depends how close I am to the end of my career.
These guys are nanoseconds. If once you get to that group,
That's right.
yeah.
But I would love to fly into the vicinity of such a thing at the end of my life if I knew that I have a day left, Wouldn't you?
When I have a nanosecond left, yeah, I'll be quite happily I will go, yeah.
You wouldn't waste an hour. Anyway, thank you so much.
Right, thank you, Avi. Yeah.
Yeah, I had a question about this. So what you described at the beginning, that you can see these things as essentially hydrogen atoms.
Right.
So their spectra will be modified
Very
by the
different.
mass.
Yeah.
So, of course, the mass is not quantized, right? So it can be modified.
range,
So
yes.
you don't really, so for an individual object, you get some modified spectrum. For a collection of these, you
Right.
get some kind of pseudo.
Unless
continuum.
there is a delta function in the mass distribution of
Yeah.
primordial black holes,
Okay.
in which case you will get a line.
Yeah.
But,
But
Otherwise-
if that's not the case,
yes,
nevertheless, you mentioned earlier that you're specifically interested in this hole that's not being constrained in the mass of black holes.
mhm,
So if you assume you have a large collection of these guys with certain mass distribution, would this produce a signal that you could pseudo
it
continuum
would be a continuum, yeah.
that you could detect somehow?
Well, the question is, how do you tell an electron gyrating in a magnetic field, synchrotron radiation is also not single valued in terms
No,
of its
no.
frequency, and then you get a continuum. And so if there are features in the continuum, you can say something, but otherwise it would be really difficult to separate a contribution, let's say, from the optical background coming from all the stars in the Milky Way from this thing, or, I mean,
Yeah,
if
so
it's in the
question, if you assume that that you take the view that this is dark matter, so you need a
Yes.
certain density of these guys.
right,
So if you have this density with a certain mass distribution,
There would
how
be an
much of a
intensity,
signal would
yeah.
this produce?
yeah, that would fix maybe the amplitude, but the mass distribution, as you pointed out, would make it, if it's broad, it would make it a continuum. And now it depends on which masses we're talking about, because you can get all the way from optical UV at the higher mass end of the range of possibilities to the gamma rays. And in gamma rays, it's really difficult to introduce sources. And if you see, so in principle, you can tell that there is, in fact, we do see gamma ray background coming from the center of the Milky Way galaxy, which is not accounted for. And most astronomers think it's probably millisecond pulsars that we do not resolve, but who knows? We don't have good, we don't know for sure what is the source of the gamma ray continuum. And one possibility is primordial black holes, because if you start with a mass that has a lifetime comparable to the age of the universe and it starts cascading, at any point in time, you will have a fraction of the total mass that is in lower mass black holes, because they live for a short fraction of the age of the universe. So, but you still get contributions from those guys, even without the atoms. Just Hawking radiation will give you some continuum. And I went through the numbers, and it looks like you could count for the gamma rays coming from the galactic center. And I spoke about it with Doug Finkbeiner, but haven't written it up yet.
Could you derive a spectrum?
Yeah.
Yeah, that would be it's a power law of some sort.
It's a power law in the gamma rays.
Yeah,
Yeah.
what's the index? Is there a simple?
Well, one can get a reasonable agreement with the current data, but so, yeah, but most astronomers would argue it's probably known gamma ray sources. I don't know. It's still,
Hard to separate from them.
yeah. Priya?
So very interesting, exciting talk. Thank you very much. I was wondering, right? So one of the strongest bounds on the PBHs is coming from these microlensing experiments. So
Right.
I was wondering what kind of spatial distribution could we conjure up that could completely circumvent the microlensing bounds, right?
Oh,
If all the PBHs have already ended up in the central supermassive black hole.
no, okay. So we are trying to find what the dark matter is made of. So we need a dark matter halo, irrespective
We
of
now know that, PBHs may not be a
So you're
considerable.
saying if it's a small fraction of dark matter,
Very
where
small
are they?
fraction,
Yeah,
yeah.
no, of course, that you could, in principle, not detect them with microlensing because they are a small fraction, and also do something to them in terms of bringing them, depending on their mass, of course, bringing them closer to the center.
All I'm saying is that those microlensing bounds may not be so tight.
Well,
If
they are
we do
tied
that-
on eliminating the possibility of them being the dark matter, because the dark matter is diffuse, we
Right,
know
right.
that. And the limits also come from M31 Andromeda. There is microlensing, there was microlensing with Subaru,
Yeah.
that put very tight limits. So it looks like above 10 to the 22 grams, it's excluded. Very massive dark matter made of very massive black holes, like 10 to the 3 solar masses or above, is ruled out by other arguments that.
Well, 10 to the 6 is ruled out because of the anisotropy that you would see them punching through disks, galactic disks.
Yeah, and
things like
also
that.
if you try to make dwarf
Galaxies.
galaxies, then it's a small number of black holes that you can include, and then you wouldn't see, you would see the effect of discreteness in the masses. Any other? Okay, Ramesh, and then Shil.
Yeah, the early part where you were talking about the accretion. So, the general point is very obvious and very clear that if the atom is bigger than the black hole horizon, you can't just treat it like a fluid or a collection of particles. So all the new effects you talked about are in that limit where then you have to look at it as a quantum problem, look at the wave function, overlap with the Schwarzschild volume, and it's a
Exactly.
beautiful calculation. I'm wondering, where does the transition happen? Where can you just use the standard
Oh,
accretion? Is it
Above-
just when it becomes smaller or?
no, it turns out to be just around the upper edge of their window that allows dark matter. So it's 10 to the 20 grams or so. Above that, 10 to the 20, 10 to the 21 grams. Above that, on the accretion, the standard treatment is fine.
Fine.
Because the black hole is big, the mouth is big enough.
Okay, but it's really a question of the mouth.
Yes.
So when the horizon radius is few times or 10 times
Then it's
an
okay.
angstrom,
Yeah.
you're
No-
all
no
right.
problem.
Okay, so it really is that sharp.
Yes.
There isn't a whole transition region covering a few decades where things are
This is
modified.
interesting. I haven't looked at the transition
Yeah.
and how quick it is.
Yeah,
Yeah, that's an interesting follow-up.
okay, very nice, yeah.
I just want to make a comment about something you said earlier about the opera experiment.
Yes. Do you remember that?
Of course, I remember that.
2012?
I
Yeah,
remember very well because many of us who work in timing
yeah.
realized there had to be a cable somewhere, right?
Oh, really?
Well,
You-
it was
you
the
knew
simplest
that-
explanation that there was.
Well,
some-
but the sun people made a splash. They did not anticipate that they.
But then they fired the
but
people.
they
Then they
didn't-
found it.
Yeah, but they didn't talk to us.
They're no longer sun.
So it was a fiber optic. Are you familiar with the details of the?
I know some
So it
of
is not
the
sun
details,
people.
It seemed like it had all the makings of a calibration cable problem, for,
So you realized that before they admitted that.
well, it seemed very highly unlikely that was the answer.
Why?
Because I just know how easy it is to have these kinds of effects creep
Right.
in.
Yeah, but why wouldn't they check for it beforehand, before announcing? Because that's
Because
embarrassing.
I don't think that CERN, they don't do it for a living, right? They don't.
It was actually an experiment outside of the territory of CERN. It
Yeah.
was in Italy or?
So the travel, the
Yeah.
neutrinos were traveling to the Gran Sasso.
Yes.
The underground.
Was it the
planets.
Italians that were slowing them down or?
No, wait, there is a very funny thing about that. So
The what?
there is a very funny thing about that episode. The neutrinos were traveling between the CERN and the Gran Sasso. So it's like 600 miles, something like that. So when the announcement came out, the Italian Ministry of Education made a big splash press release saying that we are so proud of our scientists that worked on that. And actually, the Italian government funded significantly the tunnel that was built between the Gran Sasso and the CERN, but there is no tunnel. So it was completely invented, the whole thing. But
Sorry. You mean they lied?
yeah. Just make up like a tunnel of 600 miles.
How else could the neutrinos get? But the main point was that I remember that people lost their jobs.
Yeah.
Oh,
Oh,
really?
they were fired.
Yeah, they were.
Oh,
fired.
really?
And so going
I
back
didn't know
to your
that.
earlier
What,
comment,
were they government employees or were they like?
I don't know the details.
No,
They thought,
universities
the
cannot
details.
fire.
They were scientists.
Well,
who-
Yeah, but you can't fire a professor. Can you fire a professor for making a mistake?
It all be done.
We don't go there.
Suppose, Peter, suppose,
We should do the experiment.
suppose you claim that neutrinos are faster than light. Will Garber, can Garber fire you? So there might.
I don't know about the of course part.
I'm pretty sure somebody lost their job over that offer.
Yes, yes.
And I was
No.
just saying that at the very beginning, you said we don't know what the dark matter is and we're not doing our jobs. So maybe there is hope that, some of us will be fired soon.
Yes, please.
There's a question on Zoom from
Yes.
Julia Arenas. Julia, I'm just gonna read it out. So, can ultraviolet dark matter particles in the primordial black holes get produced via black hole superradiance?
Yes, that's an excellent question. In fact,
Could you repeat that?
yes, I'll repeat that. Can primordial black holes evaporate as a result of superradiance? So superradiance is when you have a spinning black hole, and the history of superradiance goes back to the early 1970s. Saul Tokolsky and Bill Press were working on it, and also Zeldovich in the East was working on it, and they realized, and in fact, we should really be grateful to Zeldovich, because without him, according to Kip Thorne, who visited the Black Hole Initiative recently, Hawking would never come up with his calculation unless Zeldovich told him that quantum effects near black holes could be important. And the reason Zeldovich said that is because he was working on superradiance. And superradiance basically says that, when a black hole is spinning, there are modes that can couple to, it depends which field you're thinking about. It could be if the black hole is coupled to electromagnetism, then you could excite modes in the vacuum that would spin down the black hole and radiate the energy, the rotation energy. And as it turns out, in 2012, I had a postdoc named Paolo Pani. And I came up with the idea, because he told me that superradiance, in principle, if you have electromagnetic modes that you want to consider, all you need to do is surround a spinning black hole with a mirror. So you take a spherical mirror, surround a spinning black hole with it, and if it resonates with, so what ends up is the electromagnetic field that now has a boundary condition of the electric field vanishing on the mirror and because of the reflection, then you have some modes in the system that can extract the rotational energy from the black hole and create a black hole bomb. So if you ask, how can you use a black hole for military purposes? You surround it with a mirror, a spinning black hole, and you get an explosion. Okay, that's what Tokolsky and Press showed in the Nature, in the 1970s, early 70s. So now I realize, okay, but if I consider primordial black holes, go back to the early universe, the universe was filled with a plasma, meaning free electrons, okay, and protons. And free electron, in a plasma, you can get the effect of a mirror. All the photons with frequencies below the plasma frequency are reflected. That's how a mirror works, by the way. If you look at the mirror, why is the mirror reflecting your image? It's because in the visible band, these are photons bouncing off your head to the mirror, and the mirror has a silver metal membrane sort of in the back, where the plasma frequency is higher than the visible band frequencies. So a photon getting to this conductor, the silver plate, sees the plasma free electrons in the metal with the plasma frequency above the frequency of the photons. The photon cannot penetrate and it gets reflected. It cannot propagate in such a plot. It's like the plasma frequency is like giving a mass to the photon. If the mass is bigger than the energy of the photon, it cannot really propagate in that medium. It gets exponentially suppressed because the energy is smaller than the mass. So the photon cannot go into the medium and it bounces back. So that's how, when you look at the mirror in the morning, that's what happens, okay? Now, in the early universe, there was a plasma, and that can be regarded as a mirror. So if you put a primordial black hole, as long as it has some spin, which is very likely to be the case, because, why would the spherical region be perfectly spherical and collapse to a Schwarzschild black hole? So there would be some rotation from neighboring regions. So if there is a spin, what will happen is you can find a time in cosmic history where the plasma frequency was just the value needed to reflect electromagnetic waves such that superradiance would extract the rotation energy of the black hole, because the plasma frequency squared goes like the density of the plasma, and the density changes with cosmic time. As the universe expands, the density of electrons goes down. So for those primordial black holes that are more than, we calculated, I think, about 10 to the minus 10 solar masses. For those black holes, there was always a time in the history of the universe where the background plasma associated with the universe was acting as a mirror. And that would mean that these black holes would lose their spin energy and heat up the cosmic microwave background. If they do it late and they heat up the cosmic microwave background, you'll get a deviation from black body. spectrum in the cosmic microwave background. And so we ruled out black holes at a much better, much tighter limit. We ruled out black holes above 10 to the minus 10 or so solar masses, much tighter than other constraints that people derive, just from the fact that if such black holes made a small fraction of the dark matter, they would distort the microwave background at a level more than COBE constraints. So the COBE satellite from, I guess it's a time that many of the people here were not born yet. That was 93. I don't know. How many people were not born in 93? Okay, it's half of the audience. So before you were born, there was an experiment called COBE that was the first to detect microwave background anisotropes, and the Nobel Prize was awarded for it. But it also detected, and since then the limit was not improved. It detected the most perfect black body ever detected by humans. And that's the microwave background. And the limit of deviation on the deviation is 10 to the minus 5 or so from a black body spectrum. So that implies that the microwave background was not distorted by primordial black holes that had super radiance extract their spin energy. So that to answer the question, yes, and that's an excellent question. We wrote a paper about it, but it's from 12 years ago, 13 years ago. You can find it, Pani and Loeb.
All right, so it's time to thank our speaker again.
Great, Avi. Very